Hey programmers, welcome back. Right now I want to talk to you about JavaScript's event loop. So we should understand that JavaScript is really the language that makes our web pages dynamic and interactive. Now, if we think about the ways that a user could interact with a modern web page, they can do things like scroll or click buttons and even enter some keys. So the question we want to answer, right, is how does JavaScript handle these events? And events can even be things like timeouts expiring, which we've explored a lot in previous lessons. And what you should probably know is all these events of like keys being pressed and buttons being clicked, these are indeed asynchronous because we cannot predict when a user is going to hit the buttons. And so the way JavaScript is able to really handle all these events is through its model of execution, which we call the event loop. And while the event loop may be a term you haven't heard about previously, you're actually somewhat familiar already with it. That's because a piece of the event loop actually consists of the call stack, which we studied previously. And so we basically already have half of the event loop down. But we're also going to need to understand the message queue because both the call stack and the message queue interact to form JavaScript's entire event loop. And so, what is the point of the message queue? Well, I'd say the purpose of it is to really track the handling of events right. So, let's try to recall what we just mentioned about the call stack. The call stack is the structure used to track our functions. So, think of the call stack as tracking like the current task in progress, whereas the message queue is sort of like a waiting line used to track the handling of events. So let's say our computer is currently doing a task, right? And we have some information on the stack. And until that stack is free, we can't process any more events. So one thing I try to keep in mind is the call stack is what we use to kind of track the in progress tasks that are actively being worked on. Whereas the message queue is kind of used to store tasks that can't be fulfilled yet because the stack is busy. But once the stack is available, we're going to take a message from the queue and process it on the stack. And so, like its name implies, the message queue uses an underlying queue data structure, right? And it's actually really basic. So imagine a queue is just like the line for a checkout at a grocery store. And so in a line at the grocery store, you enter from the back and you leave through the front. And in the same way, we have an operation called on queue that we can use on a queue. And what this does is it allows us to add a new item to the back of the line, the back of the queue. And on the flip side of that, when we dequeue something from the queue, that means we're removing the frontmost item. And what's kind of nice about a queue is that it's fair. It's sort of a first come, first served basis. And with these queue fundamentals in mind, how does that apply to our message queue? Well, for one, we call the items that we store on the message queue messages, of course. And when a new event occurs and the runtime is busy processing another command, we add a message to the queue. And on the flip side of that, when the runtime is finished its current command, that means it's available to start processing something else. So that means the next message is dequeued from the queue, and then we place it in the call stack. If you're having a hard time visualizing how these message queue rules apply during the runtime of a program, don't worry. We're actually going to trace through how the message queue will change during this program I have on the right hand side here. And so what we're going to do is trace through this program in terms of the operations that occur on the message queue, but we're also going to have to take some insight into the call stack as well because they interact a lot, and it only makes sense when we combine the call stack and the message queue together. If we take a look at my program on the right-hand side, we have some functions built out. First thing we'll have to know is for this something slow function, I'm going to assume it takes a long time to complete, right? So for the example, let's say about 4 seconds. And we're going to assume this function takes this long to basically illustrate how the message queue has to wait until the current task is fulfilled. So this is going to be our task that takes some amount of time. And aside from that, I have a nice classic foo function that prints a message. Then I have a bar function that also prints a message, but makes a subsequent function call. So the first thing I execute is line 20, where I set a timeout for foo for 1.5 seconds. And for the purposes of this trace, we're not going to draw out the stack frames that would actually occur for the set timeout, because the set timeout is a function, and that'll make things a little too confusing, right? So when we set the timeout for foo, we know that foo won't actually be added to the stack, because when we talk about the call stack, we only add things to it when they execute. And right now, foo won't execute. It'll execute about 1.5 seconds later. And in the same way, we don't manipulate the stack or message queue for bar. When I hit line 22, that's just a regular synchronous function call, and so that will be processed on the call stack, right? Like I mentioned previously, when you call a function, you add a stack frame for it right on top of the call stack. So that means right now we are processing something slow. But notice that foo is not on the message queue and bar is not on the message queue either. In our previous slides, we said that you only add a message to the queue when the event happens. And technically, the events for foo and bar occur after their timer is done, right? So nothing happens right now because something slow is still being processed. So with this timestamp in the image of 500 milliseconds, we're going to assume that we have a snapshot of the call stack and the message queue at this point in time. The important thing to notice is this snapshot would be before both foo and bar have executed, but after something slow has begun to execute. So fast forwarding in time a little bit, let's say we're at the 1000 millisecond mark. We know that something slow is still going to be processed because we assumed it would take a total of 4000 milliseconds, right? So it makes sense that it is still on the call stack and it'll be there as long as it's being processed. But since we're at the 1000 millisecond mark, that means the timeout for bar has been triggered. Time is up. And so the bar function, or really a message representing the bar function, is going to have to wait on the message queue, right? And that's because the bar function can't be processed immediately because something slow is still on the stack. It can be helpful to think about the message queue as like a sort of waiting area. Fast forwarding more still, let's say we're at the 1500 millisecond mark, and that means something slow is still on the call stack, right? So it's blocking our execution. And so foo is going to execute because its time is up, and we actually on-queue another message representing the foo event onto our message queue. And notice the pattern here. So when we on-queue something, it goes to the back, and that means foo would be behind bar. And that's actually really nice because we want to maintain the order of our messages. So in the event that the call stack becomes free, we should really execute bar first and then foo afterwards. So at the 4000 millisecond mark, we know that something slow has finally finished executing and has popped off of the stack, and then bar is now on top of the call stack, right? And then from there, we know bar is going to process. So notice that if I look at the code on the right hand side, it's going to have to print a message and then it's going to call a function called baz. And so this really obeys our regular call stack rule. If I have to evaluate bar on the call stack and it makes another function call, our golden rule was that when you make a function call, you have to push another stack frame. That means I need to push another stack frame for baz. And then from there, baz will print, and once it returns, it will return back to the bar function. And when we return, we pop off the top frame of the call stack. So that means bar is now back on top. And so at this point, we'll say that bar is basically done executing, right? Because we return out of this function, in which case bar would be popped from the stack, and now foo would replace it on the stack and would actually be evaluated at that point. And then from there, we print out the foo message and return from foo, which means we end up with an empty call stack and an empty message queue. But with that, that's the full trace of the event loop for this program. So key things to take away are the call stack is where we actually process things and do work. So it represents the tasks that are in progress, whereas the message queue is used to track the events that we need to handle later on once the call stack becomes available.